Then we will have a break, and then there will be another informative session which will be taken care by Deimos, who will give a 50 minutes presentation. And then at 5 o'clock the bus will start where he left us this morning and bring everybody to the, not to the hotel, but to the Libreria Saggi, the bookstore where will be the public outreach event with Andrea Milani and Max Basile. So, fai una pausa quando vuoi tu.
Okay. Thanks, Alessandro. Well, this is the second part of the talk which started yesterday. The talk, as probably you remember, was divided in three main subjects, and we actually stopped at the end of at the middle of the description of some tools for space debris analysis during the re-entry. So basically, let's recall what was the one of the basic things that we said. All the tools can be classified in two different kind of tools: the object-oriented and the spacecraft-oriented codes. Most of the tools are object-oriented, and basically what they have is that the spacecraft is basically decomposed in a few elementary elements. And for each element, there is well, this decomposition is done at certain predefined altitude, and then each element is followed on its own during the trajectory with analysis of ablation or well, mostly ablation. And then there is the spacecraft object. There is only one tool at the moment, which is the European Scarab one, that actually performs a very, well, comparatively high-level code where, well, all the models involved are at a higher level, aerodynamic, aerothermodynamic, also the trajectory is simulated with higher fidelity approach, let's say, and there is no outside decision or a priori decision on the breakup or the ablation, because everything is done well, melting or breaking appear when some of phenomena make them to So we've seen yesterday the DAS and the ORSAT tools. There are well, at the moment there are many different tools. These are the DAS, ORSAT, and the Scarab are the one which are more famous, and actually the one that for which we can have some more details. There is also the SESAM, which is a European tool, which basically is very similar to the ORSAT, to the American ORSAT, with some exception. For example, there are well, the shapes, the elementary shapes that are considered are only tumbling or spinning. There is the lumped thermal mass model, but with a different melting model. The material database is temperature independent, so simplified, no oxidation, and they have some simplified subsonic drag coefficient, which is, for example, simplification is just the coefficients are just 50%. Drag coefficient is just 50% of what is found for the hypersonic. And there are also simplified models for this steady stagnation in flux. And another thing that changes is the bridging function between the continuum and free stream regime for the computation of the flux in the transition region. So, and there you can see the different bridgings more or less are the same. And actually, it is very difficult to understand which one could be more correct than the other. Let's talk now. So, SESAM is just a module in a much bigger code. Let's talk about Scarab. And what the information that I will give are information which can be found online. Scarab actually was meant to be given by ESA to all the national space agencies, but this is not actually probably not implemented yet, and many of the agencies and also the companies working in space and working in this kind of analysis are making their own tools, basically. Tools which are not similar to Scarab. Nothing is similar to Scarab. Now you will see why. Scarab is quite complex, high fidelity, but quite complex. So here you can have an idea of what Scarab has been developed under ESA contract in the last 15 years, well, for 15 years. In Scarab there is an implementation of aerodynamic and aerothermodynamic models which can actually handle very complex geometries, not simple shapes. There is a realistic breakup model, and there is also consideration for the shadowing, so the aerodynamic and thermodynamic aerodynamics, especially take into account the fact that during the flight some of the parts can be shadowed by other parts of the vehicle. Here a list of one of the things is that Scarab needs a very complex and has a very complex CAD model where which allows the user to create a realistic or quite realistic model of the spacecraft. There is the trajectory uses a 6 degree of freedom flight dynamic analysis, and basically all the models are quite high fidelity with, as I said before, breakup is done in a realistic way. So considering the stresses, and so the joints and parts of all elements are considered, well, they start to break up when there is when the local stress exceeds some of the limits. This is an example of elementary shapes that are considered in Scarab. Scarab has a CAD which follows a hierarchical approach. So all the complex systems can be composed by subsystem, and all the subsystems can be composed by other more elemental objects. And the objects, as you can see, are not just spheres or cubes, but are also alloy objects, so with holes. And this is an example of what are the models of Scarab. So totally panelized models. So it is, well, actually it is more than panelized. It is pixelized in the sense that each element, well, the external panels are used for aerodynamic and aerothermodynamic analysis. But each one of these is a three-dimensional element. The three-dimensional element which are used for the thermal analysis, structural thermal analysis, and the breakup model. So, material database. Scarab comes with a quite well-defined database of materials with which has, and all the physical properties of the materials are both the temperature independent and temperature dependent characteristics. A characteristic that makes it quite unique also is the fact that people who implemented it do not only consider the solids, but they consider also what is inside, for example, liquids in the tanks. And they do not only consider metallic elements, but also try to model the behavior, the mechanical and thermal behavior of non-metallic and non-isotropic materials. So there are some assumptions, but basically what they do is that with after a series of assumptions, they are able to quite well model liquid and gases contained in tanks. With some of the assumptions, the fact that there is no sloshing, there is the fact that what they have to do is to model some of the characteristics of the element, taking into account that the elements are liquid, so cannot, for example, liquid or gases, so they cannot are virtual solid and cannot take forces. Some of the characteristics are fixed for the mean operative point of the tank. A lot of effort, as I said, has been spent to model non-metallic materials with all the problems that it takes in, because the behavior of non-metallics can be totally different. So the melting melting points could be, melting characteristic could be totally different again. And also plastic materials are considered. And for plastics, there is the fact that there is no melting. They should not consider melting. They should consider the fact that plastic materials do actually destroy are destroyed in a stranger way, not just melting as metals, but a mix of sublimation, oxidation, and other chemical processes. And also, as I said, model of non-isotropic properties. Okay, so as I said, the spacecraft is composed by a large number of elementary shapes, and each shape is pixeled. They call, well, somewhere volume elements which are called voxels. And these voxels are used for the thermal and aerodynamic analysis, in the sense that, for example, for each element there is a thermal analysis, and there is a melting analysis, and every time that one of the small elements is melted, is basically removed by the spacecraft, by the entire model. Perturbing aerodynamic forces and moments are determined by the integration of pressure and stresses on the surface. So for each element there is also the information, if it is part of the surface, if it is part of the internal, or if it is part of the internal phase of the considered element. As for the other models, there is also here in SCARAB the approach to consider three different flow regimes, both for the aerodynamic model and for the thermodynamic model. So there are models for the free molecular flow. There are models for the continuum flow, simplified models, which are used to compute coefficients of pressure and coefficient of shear stress. And there are, for the transition region, again, some bridging functions. In particular, for example, here, this is the expression that gives coefficient of pressure for and coefficient of stress for the free molecular flow. It is much more complex with respect to the others that we've seen. It is, but it takes into account, uses these Schaffen-Chamber accommodation coefficients, and the coefficients are in this way a function of free stream, some of the free streams conditions, but also function of the normal component of the inclination of the local surface. So this gives the CP for each of the small elements, and when then integrating on all the elements, there are the we can have the actual forces which enter in trajectory optimization. For the hypersonic continuum flow, there is implemented a modified Newtonian approach, which is a little bit more complex than what we've seen yesterday, because, as I said, that was the easiest approach for the to make the Newtonian approach realistic, or the Newtonian method realistic. But there are also other kind of approaches. For example, if instead of considering 2 CP max cosine of theta, here there is a different, there are coefficients which depend from the specific heat ratio, the Mach number, and the inclination of the surface with respect to the velocity. And here there is also the fact that the shear stresses are considered 0, which is a good approximation for hypersonic flow at a very high altitude. And there are bridging functions, as I said, to convert, well, to obtain from the coefficients in free stream and continuum regime the coefficients in the transition regimes, which are function of a particular Knudsen number, which is computed on the basis of free stream conditions, density, and stagnation point temperature and viscosity. So it is a mixed Knudsen number. It is not the free stream usual Knudsen number. The same kind of approach is used for the aerothermal analysis. So basically, to predict what is the heat flux for each one of the small panels. Basically, in literature, it is reported that for free molecular heating, well, the formula here, and it is. I report here what is the expression for the Stanton number, how the Stanton number is computed. So the Stanton number is proportional to the heat flux. So basically, all what they say is that what is implemented inside is the computation of the Stanton number, and then from the computation of the Stanton number, local Stanton number, it is possible to, using that expression, to obtain the heat flux for each one of the elements. So, for the Stanton number in free molecular heating, there is, but it is not clear which one. There is an expression which is similar to this one. While for the continuum there is this hazy expression for each one of the panels. Okay, so this is something that should be applied locally for each one of the panel, taking into account how the panel is oriented toward the free stream condition. Where here it is the Reynolds number, which is another adimensional number considered in aerodynamics, which is a ratio between the density, the velocity, the radius at the nose, and the dynamic viscosity of the fluid, considering the stagnation temperature, and for because what they also implement is viscosity law as a function of the local temperature. This is something that will be presented more in detail by Piyush, but because he's basically he's working on this to make our own tool. Basically what you can see here is how the models compare the results given by the models compare with if we use different approaches. So we have the red curve here, which is the Scarab model. Then we have the Fay-Riddle model, well, one of the implementation of Fay-Riddle model, and another model, and some computation for given by DSMC codes. If we consider here, there is the mass density. This corresponds to a graph that goes from roughly 83 kilometers to 230 kilometers. So free stream regime here for sure, and here we are in the basically in the transition regime. So this is what happens. This is what is considered for the thermal analysis of each one of the pixels, each one of the voxels. So basically, it is taken into account the heat flux that comes from outside in one of the faces, the face which is facing the flow. Then there is it is taken into account the fact that the same phase is irradiating. It is also taken into account that there is conductivity, thermal conductivity with other elements of our spacecraft. And this actually is this gives actually the balance between the balance between all these components gives the temperature and the heat which is stored inside, and from this it is possible to compute the melting point and to perform also the melting analysis, the partial melting analysis. There is also database. Well, models take into account also the bank angle variation. There is also computation of some lift, which is not clear how it is done, and they implement a lot of atmosphere models inside. So this is basically what is Scarab. I hope I give you the idea of how complex, how more complex is with respect to the other tools that we've seen yesterday. Here I will use. It is not mine. I cannot perform any comparison among the tools because I do not have them. But times to times. Someone who has Scarab and access to the other is able to perform comparison. This one is one of the most recent works. So here there is the schematic description of what ORSAT and Scarab have implemented and which are the differences inside. What they did was to apply the both tools to the same test case, but as you can see, the same test case was modeled quite differently in the two different tools because they have different way to model different possibilities. So you can see that there is a very detailed model here in Scarab and a quite simplified one in ORSAT. Now, so let's see which are the results. So these are the results, the rough results that they have. So in ORSAT, there are 21 surviving components with a casualty area. Remember the casualty area that we talked about yesterday, that is basically gives a measure of the risk on ground to injure people, which is 15 square meters. In Scarab, as we were actually expecting, there are less surviving components, and there is also a smaller, 3 times smaller, more than 3 times smaller casualty area. Well, I would expect something like this because, as we said, all the object-oriented codes are more conservative. So it is expected that ORSAT could give a higher, much higher casualty area and also much higher number of surviving elements. No?
Do you remember what is the limit, the acceptable limit of the VCA? 8 meters?
8 square meters.
For
Oh, well,
one
that
is
was...
inside, for another one is outside. It's not acceptable. So that's the problem at the end.
Yes. Well, but remember also that 8 meters square is a limit which depends also on the year of the mission. Okay. So it was 8 many years ago, but that's true. If that is the limit, one says that it is fine, and the other one says no. Okay, but that is the reason why.
Yeah. But so, okay, with Scarab you can do anything, but with ORSAT you can remodel the
yeah, well,
software and solve the problem.
Yeah, but actually what they did was to correct in a proper way the results. So ORSAT, as we've seen yesterday, is used to have an upper, ORSAT and DAS are used to have an upper limit on the risk. So if actually, as it is in this case, ORSAT says that it is too risky, then some more deep analysis should be done. Otherwise, for sure, all the other approaches will give something. In this case, what they did actually, well, they analyze also all the surviving fragments, and they see which are the objects surviving in ORSAT and not surviving in Scarab, and etc. But mainly. One thing that actually they did was to adjust some of the methods affecting both codes, and this small modification brought to from 15 square meters to 6, and then to 5. And for Scarab actually. Brought from 4.4 to 5, and on the basis of this last result, they can basically claim that both tools are good, usable, and at the end of the day, it is still not possible to say which one of the methods is correct or not, if there are discrepancies. This is basically what happens with these tools. So the fact that Scarab and all the others are not freely available has pushed agencies and research groups to basically work on their own code. This is, for example, the BRISC is a tool for re-entry risk analysis developed by CNES. I found only one paper on this subject, so I'm not really sure if they are still using it or if they want to use Scarab. That is not clear, but for sure they worked on it and they developed, and it is very similar to ORSAT, which is the easiest thing to do. Another thing, it is not only agencies or research centers. There is also companies working on this. For example, Deimos has a debris. It's called debris. It is a tool which is inside their planetary entry toolbox. It is probably similar to ORSET, but there are no details on it. And basically, the only paper that the only paper available where I found this tool mentioned was a paper where this debris tool was used to simulate asteroids and not debris. So the bridge between this gives me the leverage to move to the other topic, basically. So the asteroid entry. As I said, Deimos used their tool which was developed for debris or for the entry of spacecraft to simulate asteroids and actually to simulate the Chelyabinsk meteor. But in reality, the fields are quite different each other, and they are also approached, up to now, they have been approached in different ways by different people working in different areas. While on space debris, it is mainly space agencies, aerospace companies working on it, and so aerospace people. For asteroids, the vast majority of the works and the vast majority of models have been developed by geologists and planetary scientists. So two different approaches. Two different worlds that actually Stardust is trying to put under the same umbrella. Differences. Well, I suppose that anyone in this room knows which are the main differences between the asteroids and the space debris, and why up to now they were kept separate. There are different energies involved, different velocities. Then an asteroid, space debris is some meters in diameter with orbital velocity. The asteroid could be anything up to kilometers, traveling up to 70 kilometers per second. Well, comets are 70 kilometers per second. So this brings to a totally different phenomena, totally different models. Another thing is that for space debris, more or less, we know what is the material involved. For asteroids, we can guess, but we do not have an idea of what is the structure, basically. If there are already some creeps, if there are already some defects, and basically the fact that they are stone, rocky, or plain iron makes the mechanism of fragmentation totally different from what is actually in the debris. So there are actually some very high fidelity models that have been developed mainly by Russians, starting from the 70s. So hydrodynamic codes. But what I would like to describe in the remaining of the talk is actually how some of the simplified models were basically created, and how they are used or can be used for analysis or prediction of meteoroids' evolution in the atmosphere. So the sketch here comes from a publication back in the 80s, and it is one of the mostly known publications in this area. There are two different approaches which can be used and have been used actually to describe the motion of a meteoroid. The first one is to consider the meteoroid as a strengthless liquid, and so what is used is the hydrodynamic approximation. Another, and there are many simplified semi-analytical, semi-empirical models which have been developed in the last 30 years, 40 years. And another one, different, consider actually the asteroids as a fragmenting object, and fragmenting objects which interact each other. And so what is studied is the evolution of the fragmentation of single fragments, which then are followed in their trajectory, more or less like debris. Well, all these models were developed by geologists and planetary scientists because what they wanted to do is to have some sort of reverse modeling. What they were having in front of them were evidences of craters. And so what they wanted to do is to find the characteristics of the asteroids which created the craters. And for example, and all these tools both approaches were developed to explain some of the evidence that we have in Earth. So some of the grounds, some of the craters, the fact that some of the craters are not unique, some of the craters have sub-craters around, have some small pieces of materials around also without craters. So all these kind of things made the people to think about the fact that there is fragmentation, and this fragmentation can actually follow different ways to appear, can follow different ways. So many years ago, the first thing was actually the first model was developed to simulate an asteroid which does not actually fragment. It ablates, but do not fragment. But then other approaches appeared. One is called separate fragments, okay, appeared in the late 70s and 80s. And the second one is this pancake model. Okay. Now what I'm going to do is to use the original papers in the 80s for the separate fragments, and that in the 93 for the pancake, and basically explain why people develop the model, what the model are able to predict, and which are actually the limits of the model. They can be used, and are used actually still today, in all the simplified models that we have which are implemented to simulate asteroids. The alternative to the simplified approach, as I said, is to use a full hydrodynamic model, and which actually, depending on what you implement in the hydrodynamic models, you can have different approaches. So if the meteor is considered as a strengthless continuous body, then you have a certain evolution. or you can suppose that there is a cloud of fragments, then you have another kind of evolution. And these are pictures borrowed by this publication here, where they actually compared the result of the simplified models with the results of the hydrodynamic models. The fact is, as Dr. De Stefani said, the hydrodynamic model to be used is an high fidelity model, and so can give high fidelity answers, but it depends on the data that you put inside. If in this case, for the asteroid you do not know almost anything, or there is a huge amount of uncertainty, then doing a very high fidelity simulation do not bring to precise results. So basically, so what is the approach? Is an engineering approach. So the models are used to basically put some bounds on the fact that the asteroids arrive on the ground, is ablated, and on the speed on the ground. So for example, of course, if you simulate you use the simplified model without fragmentation, what you have is that you have the bounds, or the upper bounds on the velocity for the object arriving on the ground. If you use the pancake model with infinite spreading, and I will explain later what is the spreading, that will give for sure the minimum pre-impact velocity. Okay. What I put also here between brackets is the fact that with one model you also have the minimum pre-atmospheric mass for the reverse studies. So if you want to understand which was the mass of the object, and you have the characteristics of the crater, for example, and so a simulation of what is the kinetic energy at the impact, then you can simulate the minimum mass, the minimum bound on the mass using the very simplified model. The maximum pre-atmospheric mass is given by the pancake. So these are basically the equations, the basic equations which were used many years ago and which are still used now, which give the evolution in time of the velocity and the mass. The evolution of the mass is related to the ablation, and these are equations for flat Earth. Okay, so sometimes they can be used, some other times not. If the entering angle is very small, then this approach cannot be used. Of course, in order to have some the position of the object, there are also in this case, as for the debris, the equations of kinematic equations. So, more realistically, the Earth is considered a sphere, and so some of the equations have to be changed to take into account this, and to take into account that to be able to simulate also entering with very small path angles. The models which I am presenting here do not take into account any lift effect. Okay, but this is a minor effect, has been proved, and can be actually neglected. So let's see how the separate fragments originated. The separate fragments originated with the fact that it was recognized, but not much time ago. I found that quite curious, the fact that the idea that the asteroids could fragment is only 100 years old. And the fact that the actual modelization of the actual importance of the destruction of these small bodies, because another thing, what we are considering, or what is usually considered for analysis, are normally bodies which are under few hundred meters in diameter. If they are very small, they just ablate. If they are very big, there is no analysis to do, basically. It's just something that falls in the earth and you cannot do anything. In the range of 5-10 meters to 100 or a couple of hundred, then there is reason to follow the evolution of the asteroid and see if it ablates, if it breaks, and what are the consequences in the earth in terms of risk analysis. So the first analytical study based on observation of evidence on Earth was done by Pesey and Melosh in the 80s, and they developed actually the first model, which was then after called separate fragments. So what they recognized was that there is a strong but short in time interaction between the fragments immediately after they separate, and then they move individually as individual fragments. This is what they tried to model. So this is the original sketch that they published. So basically what happens is that when the pressure on the stagnation point of the object, considered as a sphere, reaches a certain level, which at that time was considered the strength of the asteroid, which is unknown, then there is a separation. From the main body, there is a separation of a smaller part. Okay? It is curious that the approximation gives from a sphere to spheres. But this was what was done, basically. So immediately after the fragmentation, both elements travel together, and they are basically confined in the same shock wave. Then what happens is that immediately after, after a certain time, the fragments separate, and they are no more part of the same shock wave. There is an interaction of shock wave here, which give further pressure to move apart the small object from the big one. And then at the end, there is no more interactions between the shock waves, and the fragments can be considered independently flying. What they modeled was actually what they wanted to model was this transverse velocity here. And they started, for example, saying that at certain point there will be a separation here, which is a fraction of the radius of the main body. And from basic considerations, they arrived to a formula which gives the transverse velocity as a function of the principal velocity, this coefficient here, and the ratio between the radiuses and the ratio between the atmosphere density and the meteor density. Quite easy. Going by using this, they also, and with some simplification, they also obtained what can be the spreading or the position in Y of the second fragment after some time. So after the remaining time of flight. Okay, and that gives not clear. So what they do is basically, if there is no more fragmentation, this is the time of flight remaining after the separation, and this gives actually the distance of the secondary body on the ground from the previous one. Now there is the problem of the coefficient C. There is the problem of the coefficient C, but the problem has been solved semi-empirically or empirically. What they did was actually to collect all the data that they had about craters, and basically post-processing those data, they arrived, and superimposing this formula on the data, they obtained some C constant, some C values which were in the range 0.02 and 1.5. So quite different. With sorry?
No, I will say which crater fields they use, because after that epoch, some crater fields like were known to be fake crater fields, like the Sahara Desert were recognized as not being crater fields. So if they use something,
well, they use the Canyon Diablo, the meteor crater, and a few others at the time. Yeah, but the fact is, I wanted to that there is a huge amount of research in this, and there is also a huge amount of new data coming every year. So these models, especially the semi-empirical models which are based on the available data, have to be updated every year on the basis of new things. So this is how they started, and this is the basic of the model. But then, based on new knowledge, these models should be updated, and actually are updated every year. And I will show you also some new stuff at the end, some new computations, which are actually due to the new interaction between the asteroids community and the aerospace community. Okay. Okay, so this model was developed in the 80s, was used by them to perform some small computations, to actually some reverse design, but then the first numerical models, much more complex and taking into account much more data and more realistic fragmentation, have been developed much later. 15, 20 years later. Basically, what Artemieva and colleagues did was to implement the model and to consider, for example, multiple fragmentation, which is actually not easy to do. And to consider also new conditions to start the fragmentation. Okay, something more realistic and more related to the new available data. One thing which was recognized is that, for example, the new fragmented object should, to simulate the evolution of the fragments, one thing should be considered, and it was that the strength of the fragment is higher than the strength of the parent object. And that was explained by the fact that it is smaller, there are less defects, it is more compact, and then there is this effect that should be taken into account in the simulation. Okay. So the model is applicable when actually there is separation between so in this case, when we have a clear separation, but sometimes that does not happen for a lot of objects, there is, the fragmentation do not bring to separate and non more interacting objects, but brings to a cloud of fragments that travel together under the umbrella of a single shockwave. And that is why actually people, other researchers, later developed another model, which is the pancake. And maybe we can have a...
Thank you very much.